Hello, welcome to Lesson 7, Independence and Bernoulli, some conditional probability. The first example here, we are going to roll a pair of dice once and find the probability that a sum of 5 happens before a sum of 7. So some notation here, we're going to let E represent rolling the 5 before the 7, which is what we want. We're going to let F represent rolling a 5, again, with a pair of dice. G represents rolling a 7, and H represents rolling something else, neither a 5 nor a 7. So we can split up E into pieces here. E is equal to E intersected with F, union E intersected with G, union E intersected with H. Now, this will give us back all of E as long as these sets F, G, and H yield all the possible outcomes when you roll a pair of dice. The possible sums are 2 through 12. So from the way they're defined here, F represents 5, G represents 7, H represents everything else. So because F, G, and H represent the entire sample space, we can split E up into these three intersections. So again, this works because F, G, and H form a partition of the sample space. A partition is a collection of sets that are disjoint, and their union is the entire set, in this case, the entire sample space, 2 through 12. Now, these sets, F, G, and H, are disjoint, so each of the three sets, E intersect F, E intersect G, E intersect H, those are all disjoint. There's no overlap there. It's impossible to roll a 5 and a 7 on a single pair of dice with a sum. There's only one sum per roll, so it's impossible for an element to be in more than one of these sets at a time. So that is the definition of mutually exclusive events. And when you have exclusive events and you're finding the probability of a union, you can add those up without having to do any subtraction. You'd be subtracting the intersection, which has a probability of 0. So the probability of E is just the sum of these individual probabilities. E intersect F, E intersect G, and E intersect H. So let's take a look at those here. So using the formula for conditional probability, the probability of A given B is the probability of the intersection divided by the probability of B. Cross multiplying, we see that the probability of the intersection is probability of A given B times probability of B. So we're going to replace that for each of these intersection expressions. So probability of E and F becomes probability of E given F times probability of F. Same thing happens for E and G and for E and H. And now we're going to look at the conditional probabilities here. So why is the probability of E given F, why is that equal to 1 whole, 100%? So if the roll is a 5, then the 5 came before the 7. So if F occurs, then E is guaranteed. Now, if G occurs, then the event E is impossible. So the probability of E given G is 0. G is rolling a 7. If you roll the 7 first, then you cannot achieve E, which is rolling the 5 first. So that probability is 0. Now, the probability of E given H is just the probability of E. If you get neither one, the problem just restarts and you just roll again as if nothing happened. And so the probability is still as if you hadn't made any roll at all. So the probability of E given H is still the probability of E. You roll something other than 5 or 7, the process just resets and you roll again. All right, so we're going to put these together and figure out the probability of E. So we know that the probability of E given F was 100%, one whole. Probability of E given G, 0. Probability of E given H was equal to the probability of E. Okay. Now, what's the probability of F? F was rolling the 5. So how many ways are there to roll a sum of 5? There's 4 ways to do that out of 36. 1, 4, 4, 1, 3, 2, 2, 3. Now, technically, we don't really need the probability of G here because it's going to be multiplied by 0, but it's going to help us to calculate H. So what's the probability of G? G was rolling a 7, sum of 7. There's 6 ways to do that. 1, 6, 6, 1, 2, 5, 5, 2, 3, 4, 4, 3. So that's 6 out of 36. Now, H was everything else, neither a 5 nor a 7. So the easiest thing to do to find that is to do the complement, subtract off F and G. So F and G used up 10 out of the 36 possibilities, so there are 26 left. The probability of H is 1 minus the probability of F, probability of G. They're complementary events. H is the complement of F union G. And so it's 1 minus those probabilities. Common denominator, 36 out of 36, minus probability of F, 4 out of 36, minus the G, 6 out of 36, leaves us with 26 out of 36. And so we're going to now put that all together here. So from the simplified form, the probability of E was equal to the probability of F plus the probability of E times the probability of H. So notice here that the expression we want to find, the probability of E, appears on the right-hand side as well as the left. So we're going to algebraically isolate it. So the probability of E is equal to the probability of F, 4 out of 36, plus the probability of E times 26 out of 36. Multiply through by 36, clear out the fractions. Let's call X the probability of E, just to make the notation a little bit simpler. So we have clearing the fractions, multiplied by 36. 36x is equal to 4 plus 26x. Subtract 26x, that's 10x equals 4. X is 4/10, or 2/5. And so the probability of this occurring, the 5 happening before the 7, is 2/5. And now we're going to do a shortcut method here for this example. All right, so what's the shortcut? The probability of rolling a 5, a sum of 5 with a pair of dice, is 4 out of 36. The probability of rolling the 7, there's 6 ways to get a 7 out of 36. So it's 4 out of 36 and 6 out of 36. We did that back here. So the idea is that we don't care about any of the other outcomes. We just want to see if the 5 occurs before the 7. So basically, we're just comparing the number of outcomes for each of those events. And so essentially what this is saying is that for every 4 copies of 5, there are 6 copies of 7. So essentially, we're just focusing on those 2 events. So what's the probability of the 5 happening in this context? It's 4 out of 4 plus 6. It's 4 out of 10, which is 2/5. So that's a lot faster. Again, that doesn't mean that it's going to be necessarily easy to grasp, but that is a much shorter method. We will revisit these type of problems a little later in the course using series. But this technique is certainly a lot quicker than the previous approach. Let's see. We actually used this strategy in the previous problem. Just wanted to make it explicit for this next proof. So again, we have a set E and a set F. We can rewrite E in terms of these intersections. We have the circle E on the left here, and there's two regions, the portion that overlaps with F and the portion that does not. So we can split E up into two separate disjoint sections, E and F, union with E and F complement, the portion of E that's not an F together with the portion that is an F. In the previous problem, we did that, but for a situation where there were more sets. This process works because F union F complement would be all possibilities, would be the universal set. All right, so we'll do a small proof here regarding the concept of independence. Given events E and F are independent, prove that E and F complement are also independent. So what does it mean to be independent? It means the occurrence of one has no impact on the occurrence of the other. So it makes sense that if F has no impact on the event E, then the failure of F complement, also should not have an impact on E. And it turns out that E and E with F complement also, that pair is also independent. All right, so slightly different format for independence here than the conditional definition, but if two events are independent, we can say that the probability of their intersection, E and F, is equal to the product. Under regular circumstances, in the general case, it would involve conditional probability, but the conditional probability here resets to the original probability based on independence. So this is one of the properties of independent events. The probability of the intersection of the events is equal to the product of the probabilities. So we have to show this holds for E with F complement. So using our breakdown of E into E intersect F union E intersect F complement, we can apply the probability here, and because these sets are mutually exclusive, E and F complement, there's no overlap there. It's impossible to be in both of those sets at the same time. They're mutually exclusive. Their intersection is empty. So because of that, the right-hand side, the probability of that union is the sum of the probabilities. Now, we know that E and F are independent, so the probability of that intersection, E and F, is just probability E times probability F. And so we want to show that E with F complement, those are independent. We have to break down this intersection into the product. So we're going to subtract the probability of E times the probability of F. We're going to bring that over to the left-hand side, and then we're going to factor out the probability of E, leaving us with 1 minus the probability of F. Now, that is the way to calculate the probability of a complement. The probability of F complement is 1 minus the probability of F, everything else. So 1 minus P of F is the same as the probability of F complement. And so now we have what we set out to show. We have that the probability of E intersect F complement is equal to the product of those probabilities. The brackets here are equivalent to having a parentheses, nothing special there, just indicating multiplication. And so we proved what we set out to do here, to show that if E and F are independent, E and F complement are also independent. All right, lastly here, we're going to briefly introduce a Bernoulli random variable x. We haven't officially defined random variable yet. We will get to that soon here. We did mention binomial, so we're going to kind of fit that in here. So in this kind of setup here, the definition of fitting a Bernoulli random variable is that x can only take on two values. 0 and 1 are the only possible values here. And 1 is representing a success with probability p. So the probability that x is 1 is p, and then the probability that x is 0 is the complementary probability 1 minus p. There's only two outcomes here, 0 or 1. The probability of a 1 is little p, whatever the probability is, depending on the situation. And then the probability that x is 0 is the opposite probability, 1 minus p. So a couple of examples here. Flipping a coin once, it's 50-50. So the probability of success is 0.5, whether it be heads or tails. And then the complementary 1 minus p is also 0.5. So there's a 50% chance of a 0, 50% chance of a 1. Now let's take the situation of rain or no rain. So the probability of rain, if we assume it's about 30%, 0.30, then the remaining amount would be 0.7 or 70%. If you're guessing the answer to a multiple choice question with 4 choices, the probability of getting the right answer is going to be 1 out of 4 or 25%, 0.25. So that's your little p here. And then the complementary event here, the probability is 1 minus p, which would be 75% or 0.75. So you can view a Bernoulli random variable as the starting point to a binomial. It's essentially the case where n equals 1. One trial in a binomial random variable. We can view a Bernoulli in that light. Again, we're going to more formally discuss random variables, Bernoulli, binomial, among others, in the coming lessons. All right, this concludes lesson 7. As always, please feel free to get in touch if you have any questions about the lesson or the course in general. I'm always happy to answer any questions you may have. Thank you.